Welcome to part 5 of the Best Way to Learn Python tutorial series. Today we'll be talking about object-oriented programming in Python, and most of this centers around the class construct. So because we will be doing some 2D physics and animation by the end of this lesson, we have to start up the IPython Notebook in non-inline mode. So we do IPython Notebook --pylab because we will be using NumPy and Matplotlib quite extensively, but note that I'm leaving off the equals inline. Okay, so that gives us our notebook tab interface over here. I've just started with the part 5 notebook, and you'll see up top here we have the calls for changing the behavior so that we can use a print function like in Python 3, and also the integer division just so that it looks more like Python 3. Okay, so object-oriented programming, what is that all about? I think the central concept there is a thing called encapsulation. And encapsulation, although it has more than just this meaning, it also means that you're able to somehow bundle data and the behavior that operates on that data together in an object or in a class or whatever the construct may be. The idea behind this being that it makes sense because certain operations are only valid or only make sense when applied to a certain type of data. So it makes a lot of sense to bundle these together, to encapsulate them in an object. And this is exactly what object-oriented programming does. And this is also what we're going to do today using the Python class construct. So let's say that you're using Python to write some kind of geometry drawing or geometry manipulation package. So in this package, it's 2D. For argument's sake, you need rectangles, you need squares, you need circles, you need ellipses, and you also need all kinds of operations on these shapes. For example, you would like to know where the shape finds itself, how large it is, what its surface area is, what its circumference is, and sometimes you'd also like to know when you're inside or outside of that shape given a certain coordinate. And that's exactly what we're going to illustrate today. So I'm going to start with something that's relatively simple, the circle. We understand the behavior and the math behind that quite well. And I do that by using the class keyword over here. So I'm telling Python, I would like a class, and I would like you to call it circle. In Python 2.7, we have to use, well, we should use this top level Python object called object. And what this means is I'm telling Python, my circle class is a child of object. So it derives behavior from that object. We'll get to that in more detail a little later. In Python 3, this is completely valid behavior. It does exactly the same, except that bit is optional. So you don't have to put the object there. But in Python 2, if you want a new style object, which is preferable, you put object there. Okay. Then we define, for this circle class, we define the constructor called init, underscore, init, underscore. And what this does, the constructor is always executed when I instantiate the class, or when I use the class to make an object. So let's talk about that for a while. So this class is just a definition of what such a circle might look like, but it doesn't specify anything. Just to make it a little bit more clear, let's for example say that there's a radius, and we store that radius, and let's also store the center. So I'm going to instantiate one of these circles. Well, that's a documentation, I believe, from NumPy that we're going to override right now. Let's just do that, Control Enter. So now my circle class has overridden anything else. And I'm going to instantiate an object called C1, and I do that by, let's say, invoking the circle class. And look, it's telling me there it wants me to specify the radius in the center because that's the constructor. And when I instantiate this class, I do need to give the constructor what it wants, because by definition it has to be executed when the circle class is used to instantiate an object. So let's give it a radius of 1, whatever, units are arbitrary. And let me put it, let's say, a little bit to the right of the origin, and let's say 1 unit upwards from the origin. There we go. So what's happened here is And this nicely illustrates the distinction between the class and the instantiated object. The class just describes the general behavior of circles everywhere. But it doesn't. This is not a specific circle yet because it has no radius and it has no center. As soon as I specify the radius and the center, that means I've now taken this general form, this general idea of a circle, and I've turned it into a real circle. So I've instantiated this class. I've instantiated and turned it into an object, and that object it represents a real individual circle. Now, because I have this class, I can do this multiple times. So let's just make another circle, and let's make it slightly larger, and let's put it to the left of the origin, and let's keep it, or make it, let's say, 2 units high. Okay, so now I've got 2 circles. Look, there's my one circle, and you can see it's at this address over here. And if I look at my second circle, it's at a different address. And I can also query the radius of circle 2 is 1.5 and circle 1 is 1.0. So I have 2 circles over here. Okay, there's one other thing that you should note, and that is that in Python, according to the explicit is better than implicit guideline in the Zen of Python that I showed you, I think, in the last lesson, we specify explicitly a binding to the current object. So when I'm inside such a method and I talk about self, that self will be replaced by the instance. So for example, when I instantiate the circle and I give it 1.0 and 0.5 and 1.0 as its center, inside when I say self.radius, it means that these values are attached to this instance, to this object C1. And self will always, the first parameter, which is explicitly automatically passed by Python, always represents the current instance. So the nice thing about this is that there can be no guessing or no implicit magic happening. For example, in C++, you have this, and this is just available. You don't see it anywhere. It does not specify, but it's available when you want that instance. In Python, it's all explicit. So let's say I would like to know what the circumference of my circle is. And now you see where this, or how this encapsulation could be useful. So as we all know, that's 2 pi times the radius. Oh, I need my math. We'll talk about imports in a future lesson. So let's see if that works. Let's just execute that by Control-Enter. I'll go down to this cell and then say C1 dot circumference. And C3, C1, sorry, that was C2 and this is C1. So what's happening over there is that when I call this circumference method, see, I don't have to specify any parameters because I'm calling it on the object, right? That's explicit. Python will then add this binding to that object on which I'm calling it. It will add as the first parameter to the method that I'm calling. So internally, I can now use that to query my own radius, whatever I may be. And I may be C1 or C2 or any other instance of this class. So let's continue for a little while and let's also calculate the area. And as we all know, that's pi radius squared. So it's math.pi times self.radius squared. I just execute it to define. It's almost a habit, pressing Control-Enter. And then it gets interesting because I can now also define a method that will tell me whether a certain point is located within my circle or without. So you can imagine this is useful when the user clicks on the screen and you'd like to know whether they've clicked on one of your circles. Then you can just ask all of the circles, point inside, and then the coordinate, and then point inside will either give you yes or no. Okay, let's have a look at that. So to do this, we're going to calculate the Euclidean distance from this point to the center of the circle, which we all have. And then we're going to see if that Euclidean distance, if that's smaller than the radius. If it's smaller than the radius, it means that point is inside the circle. Okay, so we break that up. I'm explicitly not using NumPy for this, although in NumPy it would be really easy. I'm doing this with basic Python, so you can see what it looks like. So my xy coordinate is passed as a tuple with x and y. So let me get out the x. So xy and then the 0th element would be the x, minus my own center, like that. And then let's do the same for y, the y distance, except then I have to change these indexes to 1 and 1. So now I have the distance on the x-axis and the distance on the y-axis between this point xy and the center of my circle. Okay, and then I use this function, hypotenuse, and then I just say, well, that's about what I want, yeah. So that's the x distance squared plus the y distance squared, and the square root of that, and that's going to give me the direct line Euclidean distance. And that's exactly what I want. Let's just call that dist, makes my code nice and clear. So now, if this distance is smaller than the radius, then obviously that point is inside, else it's not. So let's see how that works. Just Control Enter to execute this. So let's see. So my C2 circle, let's make another circle to make this a bit easier to test. Let's put a circle with a diameter, a radius of 0.5, and we put it at the origin, so at 0.0, like that. And then over here, I'm going to say C3, point inside. So the circle has a radius of 0.5. So let's say I put my point, let's see, I need to specify xy. So let's say on the x-axis 0.6, and on the y-axis it can just lie on the ground. That's not inside. Now as soon as I do that, so I say it's smaller than self radius, so this is probably also still going to be outside because it's on the actual perimeter. If I say, so now the point's inside the circle. So I hope that you can see through this example that it's quite useful being able to bundle these behaviors, so these methods that operate on the data and bundle it all nicely together in a class, that gives you these interesting possibilities. I'd also just like to demonstrate why, or what we could do with inheritance. So in this specific case, we could make our lives a bit more easy, saying, well, let's make a basic shape and call it a basic. Let's define what all these shapes share, and we call it shape. Okay. And the only thing that I can really think of in this specific example is, let's say that all shapes have a position. Now, in the case of the circle, that would be the center. In the case of a rectangle, that could be the bottom left corner, and so forth. It would be a slightly different definition, but it illustrates the point. It's slightly contrived, but I hope you get the idea. Okay, but in this case, we do the same, like that. And now, instead of deriving circle from object, we derive it from shape. So when you do this type of child class, you should be able to answer the question, is circle a shape? And only if that the answer to that question is yes, then this derivation or this kind of child class relationship is valid. So in this case, definitely, circle is definitely a shape. So now I have to change this. This init still needs the radius, and the center is also being passed, but now I'm not going to store the center anymore explicitly. I'm going to store it as position. So I could either go and say self position is center, right? So what's happening here is, because circle is the child of shape, it inherits everything that shape has, and because shape has an instance variable called position, circle also has that instance variable, and I can access it like this. Okay. This is not the nicest way of doing this. I should, in fact, call my parent constructor to do this work for me. But that is, well, let me just show you how that works. So I would, for example, go super, and then I would go my type and my instance. And then I would call my parent constructor, I would call with center. And then I don't have to do that. Because now what's happening is it automatically it finds out who my parent is, and then it will call my parent's constructor with the center that the user has given me, and we know that that constructor will then store that center as my position. And now I just have to change this code because it's still referring to center. Now I'm done. Okay, so that illustrates inheritance. So that's also a very, very, very important object-oriented programming concept. And the idea is that if you can say that one object is the other, so for example, in this case, a circle is a shape, a rectangle is a shape, a square is a shape, and so forth, then you can factor out common functionality into that parent class, and always this semantic relationship still has to hold, else you're doing something wrong. And that means that I only have to implement that common functionality once, and I only have to test it once and to ensure that it works once, and then all of the child classes inherit that functionality. And obviously, if I then make a change in that base functionality, being very careful to to stay within the relationship that this base class has with all its children, all my children automatically get that new functionality. So also, if I fix a bug, for example, in the base, that behavior is then fixed in all of my child classes. So I hope that that more or less makes clear what I can do with OOP or with classes in Python. So the general idea is that I can encapsulate data, and in this case the data is the radius and the position, and that's inherent to a circle. And then I can associate a number of behaviors, in this case the circumference, the area, the point inside, there's many more that you can think of, that operate on this data. And what happens then is I can go and instantiate that class. That class is just a template. It doesn't really, it describes the general object. When I specify its parameters, then it becomes a specific object, and then I call it that I say that I'm instantiating that class, and the result is a new object. And I can do that as many times as I want. Okay, so now back to my example. So what we're going to do, I've worked this out for you beforehand, so I'm just going to take my previous work. Well, this is more for fun than anything else, because we're not going to go in that much detail through the whole example. Okay, so what we have here, or what I wanted to do, I wanted to show you that, what classes can be used for. And I also wanted to do a bit of physics. So we're building up also on the examples as we go along. So in this case, what I would like to simulate is a bouncing ball. Okay, so for such a simulation, and I hope that you're still fresh on your I don't know, kindergarten physics, but we have to obviously know about the gravitational acceleration on Earth. And as you all know, that's 9.8 meters per second squared. Then I go, this is obviously a vector, always pointing to the center of the Earth. But because I'm working in a small room, or in a relatively small area, I can approximate it and say, well, it's just pointing downwards. Well, that will also be the case. And then I just construct, using NumPy, I construct a vector that has as the x component 0, because it's only downwards, and then minus g. So there's an acceleration component of minus 9.8 meters per second. And then this is quite interesting. This is the coefficient of restitution. So because I want to simulate a bouncing ball, and bouncing balls, when they bounce on the floor, they lose some of their energy. So they change their velocity. The velocity vector flips around, it reflects. But obviously it's not a perfect world, and some energy is lost in the deformation of the ball. So in a completely or 100% elastic ball, and that doesn't exist, all energy is retained, and the coefficient of restitution will be 1. But in my case, I've just gone and tuned it a bit, and I've come up with a coefficient of restitution. This is the ratio of the velocity after and before the bounce. So if this is 1, it means the ball hits the wall or the floor with a velocity of x, and then that velocity of x is just flipped around and it bounces away with that same velocity. But that can obviously not be the case in the real world. So that's what I use this coefficient of restitution for. Okay, so I build a room, and I want my room to be about 30 units in length or width and about 20 units in height. It's a two-dimensional room. And now I'm going to start to model my ball. So the ball that I want to bounce has an initial position. This can be anything. And I also give it an initial velocity v. You can see I'm using NumPy vectors for all of this, because I'm going to use NumPy math soon in the simulation. Okay, and I'm going to run the simulation with a delta t of 1 millisecond, so 0.001. So first I go and I create a plot over here, and then I create an empty plot. So I plot a single little dot. That's going to be my ball. That's green. Okay, and then I'm going to use the Matplotlib animation API, and what that wants from me, it wants a function that will generate new Matplotlib lines. Okay, so that's what this animate is going to do. And what happens here, I specify a bunch of time values. So look what I've done here. I'm going from 0 to 100 seconds, and I'm doing it with a step of delta t. Now remember, delta t was 1 millisecond. So what's going to happen here is that Matplotlib is going to take this list of second values, of time values, and it's going to keep on calling animate each time with a new t. So it adds delta t, and then it calls t again. So each time with 1 millisecond further in the future. Okay, so inside of animate, the first thing I do, so remember xy is the position of my ball, and then I check, is xy, has it gone beyond the left wall? So is xy 0, which is the x coordinate of my ball, is it smaller than the left limit? So that's kind of the x coordinate of my left wall. If it's smaller, then I go and I reflect it. So I basically just go and I flip around the sign of the x component. And if I did that without this coefficient of restitution, the ball would bounce away with the same speed that it bounced towards the ball. I didn't want that. I wanted to be a bit more realistic. So I multiplied with a core, and that will obviously siphon away, or that will subtract some of the ball's velocity, and that gives me a new x velocity. I do the same. So obviously these two conditions can't be true at the same time. That's why I'm using an elif. So if the ball did not go past the left wall, it might have gone past the right wall. So I do exactly the same. So then I go and ask, is the ball's x coordinate, is it now greater or equal to where the right wall is? And if that's the case, I do the same. So I just take the absolute value of the x velocity, because I'm going to multiply it with the negative of the coefficient of restitution, meaning it's going to bounce left. And it's going to throw away some energy to model the non-elasticity of that ball. And then I get a new x velocity. So I do exactly the same for the y component over here. So I just first see, has the ball gone below the floor marginally? If so, then I turn the velocity around and I bleed away some of its energy to model the non-elasticity. If that's not the case, it might be the case that it's hit the roof, and I'm also going to make it bounce downwards. So first I take the absolute of the velocity to make sure that's positive, and then I multiply it with the negative of the coefficient of restitution, so it'll bounce back down, but it's also going to lose some energy during the bounce. And then I go, now this is the interesting part, I take the gravitational acceleration, so that was the minus 9.8 meters per second. I multiply that by delta t, which is 0.001 seconds. So when I do that, I get obviously the velocity, the differential velocity. That's the delta v. And that will, in this case, it will have to be that 0.001 multiplied by 9.8 meters per second. And that delta v is very simply just added to my differential velocity. Okay, so I have the difference in velocity caused by the gravitational acceleration. It's just acceleration, so that's exactly what it does. And then I get a new velocity. And this new velocity is also a vector with xy components. I just add it to the xy coordinate of my ball. And the only thing left to do, and this is just a kind of let's say a mathematical regularization for this mathematical model, I check whether the ball, even after all of this math, hasn't by accident fallen outside of the room. It can happen with, let's say, when it's very close to the one wall and due to kind of numerical error, it could land on the outside of the wall. And I use the NumPy clip function to make sure that its x and y coordinates are located within the room. So it's going to clip it. So if it's just outside, it's going to put it just inside on the other side of that wall. And then I take that xy and I apply it to that plot, and then I return that to the animation framework. And that's it. And I have to do this plot show because it's not a notebook. So let's see what that looks like. So there you can see. That looks pretty realistic. So the ball started somewhere here. It had initial velocity in this direction. And obviously the gravitational acceleration started pulling it down. And you can see it bouncing nicely. And you can also see the coefficient of restitution you can see bleeding away its energy. So there we go. We have a very nice simulation of 2D reality, including ball bouncing and including the gravitational acceleration, and it works and it even looks realistic. And that's just really awesome about this type of programming. So let's see what happens if I bounce the same ball on the moon. So I looked it up, and the gravitational acceleration on the moon is about the 1/6 of that on Earth, as you know, and that comes out to about 1.6249 meters per second square. And I just changed that one single constant, and I rerun my simulation, and you can see that, well, we get a wildly different result. This is probably what it might look like when you bounce a ball on the moon. So it's got that dreamy, slow motion kind of falling look that we would expect, but eventually it's going to bleed away its energy and it's going to land on the floor. Okay, so that's it for my 2D simulation. And now I would like to show you what happens when we apply object-oriented programming to this idea. So in this case, I've also prepared this example for you. It's exactly the same example, except what I've done now is that I've taken all of the parameters, the data, the characteristics of that ball, and also the behavior, in other words, the updating at each 0.001 seconds, each millisecond, and I've installed it inside of a ball class, right? So this ball I'm deriving from object, and in its constructor, it's getting its initial position and its initial velocity, and it's storing those in its own, let's say, in the object using self. And then it's also creating that line for me with a single ball. I'm leaving off the color because Matplotlib will assign a different color each time I call this ax.plot. And then I have this update function, which can be called on the ball at, during that animate function. That's this one over here. That's called by the Matplotlib animation framework. And that will then go and update the ball's parameters based on bouncing and also based on the the gravitational acceleration, and then also this regularization step, making sure that the ball remains in the room. And then it just goes and modifies its own scatter instance variable. Now the brilliant thing is I can create as many balls as I want. So here I go, b0 equals ball, and I give it an initial position and the initial velocity. I do the same for the second ball. And then in my animate function, I simply call update on the different balls that I might have. And I end by returning their scatter members. And when I do this, I now get 2 balls. And as you will have guessed, it really doesn't matter how many of these I make, because I've now defined the general behavior of a ball. I've now defined the general behavior of the ball. I can just give it some new parameters. Let's give this one a bit more upwards initial velocity. I should probably use an array. I can even do that. Let's do that for you and just call this. Remember, I can use a list and I can stick anything in that list. So now I have a list called balls. And now I can do for ball in balls, ball update. And let's use a list comprehension, ball scatter for ball in balls. So what this is going to do is it's going to iterate using this list comprehension through balls, and then it will each time call, it will call this instance variables on the ball and insert it into the new array. And no matter how many balls I have in there, look. And that's the beauty of 2D physics and also of object-oriented programming. I'm going to put all of this will be on GitHub so that you can download the notebooks and you can play to your heart's content with this simulation. Okay, to recap, that was object-oriented programming or classes in Python. I showed you what a class looks like. Remember, a class is a description of that general object, what it is in general. When I go and instantiate, I'm giving it a specific instance, or I'm telling it, listen, these are your parameters, and in return for that, I get an instance, I get an object. And that's not general anymore, that's now been instantiated. And what I can also do is I can extract common functionality, and if there's an is-a relationship, a circle is a shape, a rectangle is a shape, I can then create this this class hierarchy, and I can have common functionality in the parent classes, and I can have all of the child classes benefit from that common functionality. Then also remember that the self is always explicitly specified. So when you call a method such as this on an instance, that instance will be passed automatically as the first parameter, and you get it explicitly within your method to work with. And then we made a nice 2D physics simulation with bouncing balls, and you could see by very simply applying the gravitational acceleration and this coefficient of restitution, we got a pretty realistic looking ball. And then finally I showed you how by just stuffing all of the ball related behavior and data inside of a ball class, we can very easily kind of scale up our simulation and get many more balls in there. So thank you very much for listening. This was part 5 of the best way to learn Python.